In a graph, a mouse begins its dash, escaping the cat with a lightning flash. Through nodes and ridges, the chase is on to reach the hole before the cat is drawn. But in this race of speed and fun, who'll emerge victorious when all is done?
Hello friends, my name is Iris and this is CPP in Pajamas. Thank you for joining. This is the first video on my channel that is recorded in English. All future ones will be in English. And if you find a LeetCode question that I have already solved but not in English and it interests you, send a message or write a comment and I'll try to redo it in English and cater for my smart and lovely audience. Today we will be solving question 913 on LeetCode, cat and mouse. It is a hard question, but we will turn it into very easy and solve it in the most efficient way. Let us begin. Cat and mouse. A game on an undirected graph is played by two players, mouse and cat, who alternate turns. The graph is given as follows. Graph at index A is a list of all nodes B such that AB is an edge of the graph. In simple words, the input will be a vector. Every index 0, 1, 2, 3, etc. in the vector will hold another vector of all the nodes that are adjacent to that index, to that node. The mouse starts at node 1 and goes first. The cat starts at node 2 and goes second, and then they alternate. There is a hole at node 0. So the minimum number of nodes we will have in our graph is 3. 1, 2, and 0 for the hole. During each player's turn, they must travel along one edge of the graph that meets where they are. They're to an adjacent node. For example, if the mouse is at node 1, it must travel to any node in graph index 1, because that's where you have a vector of all nodes adjacent to node 1. Additionally, it is not allowed for the cat to travel to the whole node, node 0. Then, the game can end in one of three ways. If ever the cat occupies the same node as the mouse, the cat wins because he catches the mouse. If ever the mouse reaches the hole, the mouse wins because he escapes to freedom. If ever a position is repeated, skip, the game is a draw. What did they skip? Just like in a chess game, when you and your opponent try not to lose, and so find yourself just going back and forth, to where you both have just been forever, then there's no winner, it's a draw. Given a graph, and assuming both players play optimally, we will explain this word in a second, return. 1. If the mouse is the definite winner of the game. 2. If the cat is the definite winner of the game. 0. If the game is a draw. There is no definite winner of the game. So what does optimally mean? In the first example here, we will see a smart example for optimal playing. However, simple examples for optimal playing might be if it's the mouse turn. So from where he is, he must travel to one of the adjacent nodes to where he is. And say one of them is the hole. Of course he should go there and immediately win and not start wandering around to other nodes. Or if on one of those nodes there is the cat, of course he shouldn't go there and lose. He should choose another option to go to. So these are basic examples. Or if it's the cat's turn and he has several options, or one of them has the mouse there, of course you should go there and immediately win. These are examples simple examples for optimal playing. But let's look here. In this first example, here is the hole, here is the mouse at node 1, the cat at node 2, and as we know, the mouse goes first. So the mouse has just one option, to travel from 1 to 3. So the mouse is now at 3, and now the cat can choose to go from 2 either to 4 or to 5. Of course, not to 0, he's not allowed there. So what should the cat choose? Go to 4 or go to 5? Which is optimal? Let's think. If the cat chooses to go to 4, then the mouse on his turn will go from 3 to 5. Of course, not to 4, the cat is there, not to 1, because he wants to try to win, not to have a draw. So won't go back. He'll go from 3 to 5. So now the mouse is at 5, and then the cat again from 4 has two options, go to 3 or go to 2. It doesn't matter what he chooses, whether he goes to 3 or to 2, then the mouse will just go from 5 to 0 and win. So choosing to go from 2 to 4 as the first step of the cat immediately predicts his loss. That's not optimal. Let's try again. So we know the cat, yeah? It shouldn't have done that. So let's try again. The mouse goes from 1 to 3. Now the cat will go from 2 to 5. Let's try this. So the cat is at 5. Now the mouse at 3 will not go to 5, will not go back to 1, he'll go to 4. So now the mouse is at 4, and again the cat from 5 has two options. He can either go to 3 or to 2. What's optimal? Let's think. If the cat goes from 5 to 3, then the mouse will go from 4 to 2, then the cat can choose between 4 and 5, which don't matter. It doesn't matter what he chooses, because then the mouse will go from 2 to 0 and win. So again, bad choice. Let's try again. Mouse went from 1 to 3, cat goes from 2 to 5, mouse goes from 3 to 4. Now cat will go back to 2 to where he already has been. This forces the mouse to go from 4 back to 3, where he already has been. And at this point, they're both going back and forth, and it's a draw. But a draw for each of them is better than losing, right? So this is what they are doing, and it's a draw. We return a 0. In this example, it's much simpler. Here is the mouse at 1, the cat at 2. Mouse goes first, as we know. Just goes immediately to the whole node and wins. We return 1. It's a mouse win. The constraints here tell us that the graph length would be between 3 nodes and 50, both inclusive. We know the 3 is mandatory, 0, 1, and 2, and up to 50, that's not a huge graph. Read the rest of the constraints on your own, but in summary, what they tell us is, all of them, is that the input that we are getting is perfectly valid and legal. For example, no node is disconnected. The mouse and cat can always move, everything is connected. And no node is adjacent to itself. No node is a cycle to itself. No node is adjacent to another one more than once. So we won't get in the input that that node 1 is connected to node 2, for example, by 2 edges. It's all perfectly valid and legal. Read it through. Okay, so we see that the acceptance rate is not that low. It's low, but not that low. However, not too many submissions. Okay, let's turn this into extremely easy, and we'll start with the paper, then we'll move on to the code. Let us begin by determining the term state for this game. A state is a combination of 3 values. Where is the mouse? Where is the cat? Whose turn it to move next? Who's about to play now? Let's see why all 3 values are crucial to determine a state of the game. This here is the most basic graph because it has only the 3 mandatory nodes. So here is the hole, and here are the mouse and cat in their initial positions. Now, let's say that it's the mouse's turn to play. Okay, so the mouse just does this, escapes to freedom, and wins. Mouse wins. But instead of saying that it's the mouse's turn to play, let's now say it's the cat's turn to play. Structure of the graph is the same. Positions of the mouse and cat are the same, but the only change is that it's the cat's turn to play. The cat just does this and wins. So everything is just the same, excluding whose turn it is to play now, and that determines a completely different result, a completely different winner for the game. So these three values are crucial to determine the state of the game and the winner. Where is the mouse? Where is the cat? Whose turn is it to play now? Who is about to move? Okay? Now, are there certain states of the game for which there is already a pre-known winner without needing to calculate anything? Yes, there are such states. Many. For example, if the mouse is at node 0 and it doesn't matter where the cat is, the mouse says bye-bye and escapes to freedom. It's a mouse win. Let us say this is a state. Where is the mouse? Node 0. Where is the cat? Anywhere on the graph. We know the cat is not allowed at 0. Anywhere on the graph. Whose turn is it to play? Either. It doesn't matter. In all those states, the winner is the mouse. However, if we want to be a bit more precise, and we want to be precise, whose turn really is it going to be? Either in real life? Correct. It's going to be the cat's turn for sure, because in our game, the mouse and cat are not randomly landed onto their initial positions, saying that the mouse might have landed on 0 to begin with, and now it's his turn. No. The initial positions are 1 and 2. This means that if the mouse finds himself at node 0, it is because he had just moved there. And if he had just moved, now it's the cat's turn. So while it doesn't matter whose turn it is, in real life it's going to be the cat's turn, and it matters for performance. We were going only to talk about things that may happen. Okay, so do we have more states of the game for which there is a pre-known winner without calculating anything? Yes, if they're both together, anywhere on the graph, excluding node 0, if they're both together, anywhere on the graph, it's a cat win, because the cat caught the mouse. Let's say it as a state. Where is the mouse? Any vertex V. Where is the cat? On that same vertex V as the mouse. Whose turn is it? Who's about to move? It doesn't matter, because either the mouse did this and now it's the cat's turn, or the cat did this and now it's the mouse turn. It doesn't matter. In either case, they have met. Since they have met, it's the cat win. Okay? Great. So we have several states which are already resolved. We already know the winner for them without calculating anything. Now, let us define our goal state, the state for which we need a result to return for this question. Our goal state is, where is the mouse? Node 1. Where is the cat? Node 2. Whose turn is it to move now? Mouse, because we know he goes first. This is our goal state, as we can see here, and it's the mouse turn. Does our goal state fall onto any of the states for which we already know the result? No, it doesn't, because we know the result for states where either the mouse is at 0 and he's not. He starts in the goal state is at 1. Or they're together, but they're not. They're not together in the goal state. So we will have to calculate and find out the result, the winner, if there is a winner, for the goal state. How will we do that? Well, I'll give you an example. Maybe some of you know this game of numbers where there are two players who play alternately, just like here, and they need the first number that must be said is between 1 and 10. And then every player in his turn needs to say a number that is not higher by more than 10 than the number that the other one said. And the one who says 100 wins. Because I know this game, I know that if I say 12, no matter what the first one said, the other one said, if I say 12, I win. Because if I say 12, I'll surely be able to say 23, and then 34, and then 45. Oh, I can just not say, I can say anything as long as in the middle of the game somewhere, I get to see a number that's in this structure. 23, 34, 45, 56, 67, because I need to be able to say 89. If I say 89, I win. I'll definitely say 100. What am I trying to say? I'm saying that even though there are many steps still until winning, already in the beginning, I'm the certain winner. Okay? So a winner of a game can be known way before the winning actually happens, because there is no other choice. Or like in a game of chess, a seasoned player knows how to order the chess pieces on the board such that even though it may take some time, some steps to be done, still there is no choice for the other. Whatever happens, it's a sure win for the seasoned player. Okay? Way before the win actually happens. Same here. We have the states that are already resolved. We know the definite winner for them. For each of these resolved states, we'll take one by one and go from each one step backwards and see if in that previous state that in one step led to the resolved state, there is already a definite winner. And again, one step backwards, and again, one step backwards. Every time we'll take one step backwards to the state that led in one move to the resolved state and see if we can deduce a definite winner already then. If this sounds to you like dynamic programming, then you're correct, because the states for which we already know the result, these are the subproblems that we already have the result for. We will use the results of the subproblems to deduce results for wider and wider problems until we are able to deduce the result for the big problem, our goal state. Also, if it sounds to you like BFS, again you're correct. It's a BFS, because every time from every winning state, resolved state, we go one step backwards to all of the states that could immediately lead to it and try to deduce for them. We will see this. Okay, so what will be the algorithm? We are going to understand the algorithm by examining the three different variations of the most basic graph. The most basic graph is just 3 nodes, as we know, but it has 3 variations. Each of these variations will teach us something new that is crucial for the algorithm. So once I finish the first one, don't fast forward to the code because you will be missing stuff. Okay? We need to go one by one, and only after the third one, we'll have the complete algorithm. Let us begin. Okay, so here we have a matrix. This is the same matrix as we will have in our code. We will do a dry run on it. Here we will hold the resolved state every time from the states for which we already know the winner, and we'll try to deduce to previous states and resolve them as well. Okay, so our matrix, as you can see or will see, is 3-dimensional. In every cell, I'm holding some data, but we just start with the winner. In every cell, I'm holding the winner for a state, trying to resolve the winner for the goal state. Now, why do I need a 3-dimensional matrix to hold the winner? Because a state is 3-dimensional. Where's the mouse? Where's the cat? Whose turn is it to go now to play? These are 3 dimensions. So for each such state of 3 dimensions, I need to know the winner. So in this matrix, every row is for the mouse position. Since we have in this example 3 nodes, then we have 3 rows. The mouse can be at node 0, 1, or 2. The columns are for cat position. And for the 3rd dimension, I cut each column into mouse and cat. Mouse turn to play, cat turn to play. Okay? So this is the 3rd dimension. The green question mark here in bold is our goal state. This is what we're trying to resolve. Where is the mouse? 1. Where is the cat? 2. Whose turn is it? Mouse. Who's the winner? I need to find it out. The zeros that you see here, ignore. It will come in the 3rd example. Ignore for now. Just see the question marks for who's the winner. So the green one is the goal state. But also we have some pre-known winners, and these are the little pictures. For example, if the mouse and cat are on the same node together, the cat catches the mouse and wins. So both on 1, and it doesn't matter whose turn it is, or both on 2, and it doesn't matter whose turn it is. It's a cat win. Also, we know that if the mouse is at 0, and no matter where the cat is, it's a mouse win. But see here, I didn't do this. I didn't put the mouse also here, and here, and here. Because as we said, while it doesn't matter whose turn it is, it's going to be a cat turn. And I don't want to handle and hold data that's not gonna happen. And after we write our code, I'm gonna run a test case with you to show you this. So this will return. So I just drew it on the cat's turn, because that's the only thing that might happen. Okay, so let us take this initialize matrix. Let's push all the resolved state in the queue. Let's imagine we have a queue with all the resolved states, and take one by one and try to resolve from it. So I am randomly choosing now, with your permission, because this is a dry run. I'm choosing to deduce from this state. This is the state I want to try and deduce more winning states from it. Try to resolve more states from it. So let's draw this resolved state. Where is the mouse? 0. Where is the cat? 2. Good. Whose turn is it? The cat. Who's the winner? The mouse. So this is it in the picture, and let us draw it here. Mouse at 0. Cat at 2. Whose turn is it? Next player, cat. Who's the winner? Lovely mouse. Great. Let us deduce, if we can, for previous states. So, if in the resolved state it's the cat's turn to play, then whose turn was it to play in the step that led to it in the previous state? If here it's the cat's turn to play, that in the previous state it was the mouse turn to play, because they alternate turn. So the mouse made a move from this state that you're trying to figure out onto this state that is resolved. And now it will be the cat's turn to play. Great. Now, if the mouse made the move, where were they? Well, if the mouse made the move, then the cat was just where he is. He'll move next from 2 to somewhere, I don't know. But here the mouse made the move, so the cat was just where he is. 2. And where was the mouse? Well, to know where the mouse was, we need to look at the graph and see from where he could have moved onto this state, or in other words, what are the adjacencies to where he is here in this resolved state? 0. So if we look at the graph, we see that this is the only adjacency to where he is in the resolved state. He could have only moved from here onto here. So he was at 1. So let's take a look at this together. In the previous state, the mouse was at 1, the cat was at 2, it was the mouse turn to play, so he made the move onto this already resolved state where he's at 0, the cat is at 2, now it's the cat's turn, and the mouse has 1. Great. So can you deduce already for this previous state that the winner of the resolved state is already the winner here? Most definitely, yes. Because it's the mouse turn, as we can see, and he made just one move on this turn of his. Sorry about the noise. And he made a move on this one, move on this turn, and he made the move onto winning. So already in this state he was the winner. And as we can see with our eyes, we don't really have to do this to see that he won. When we look at this graph and we know the mouse is about to play, we already see he's the winner. Great. So we have resolved a new state. So let us mark this in our matrix. Where is the mouse? 1. Where is the cat? 2. Whose turn is it? Mouse. Who's the winner? Mouse. 1, 2, mouse. We have a winner for this state. Not just a winner for this state, a winner for our goal state. This is what we're trying to figure out. So we can say that we're done and we have a result for this graph. This is a mouse win. Great. So now we are moving on to the next example. And in the second example, the hole will be in the middle. This is the second variation of the most basic graph. Let us clean. The initialization of our matrix doesn't change. It's the same resolved state without they don't need any calculations. I'm going to choose the same resolved state to deduce from. Same. Okay, so if in the resolved state the next one to play is the cat, then who just played in the step that led to it? The mouse. If the mouse is the one who moved, oh, let's draw it. Okay, this is the resolved state. Mouse at 0, cat at 2. So if the mouse is the one who moved, where were they? If the mouse moved, the cat was just where he is. Where did the mouse come from? We need to look at the graph and see all the adjacent nodes to where he is in the resolved state, from which he made the move onto this. So in the graph we see that there are 2 adjacencies to 0, 1, and 2. There are 2 locations from which the mouse on his turn could have come to this state. So we'll have to examine both. He either came from 1, doing this, onto the resolved state, or he came from 2, doing this, onto the resolved state. Let's examine this one first, this. So, mouse at 2, cat at 2, mouse turn to play, and on this turn of his to play, he makes the move and wins onto freedom. So can we say that already in this state it's a mouse win? Can we do this? Of course not, because already here the mouse is caught by the cat. He can't move to freedom, he's already caught. It's no one's turn. No one can, he lost. So I can't do this. And if we look at our matrix, then for this state, let's delete this because it's wrong. Then for this state, mouse at 2, cat at 2, mouse turn to move, there is already a winner. The cat has already won, as we can see with our eyes. The mouse can't move, even though it's 1 step to winning and it's his turn, he's caught. So we can see here that if there is already a winner for a state, we cannot override it with a new winner. This is a BFS. When we first reach a state and resolve it, that's the correct result for that state. We can't override it. So this is no. I can't deduce because it already has a winner, this state. So let's look at the other previous state where the mouse was at 1. So mouse at 1, cat at 2, it's mouse turn, and in one move, he comes to this state where he's the winner. So it's his turn and he made to move on this turn of his and won. Can we say that already here is the winner? Let's take a look at the matrix. Is this state already resolved? Mouse at 1, cat at 2, mouse turn. No, it's not resolved yet. So we can resolve it. Not only have we resolved this state, we resolved the entire question because this is our goal state and we're done. So this graph also is a win of the mouse. Let us move on to the third and very different example. Here, as you can guess, node 2 will be in the middle. Let us clean. Okay, so initialization of the metric is just the same. Let us try deducing. I'm choosing the same resolved state to deduce from. Okay, let us draw this resolved state. Mouse at 0, cat at 2, there. Okay, what was the previous state to this? Well, if it's the cat turn to move, then it was the mouse who made the move in the previous state. Where were they? If the mouse moved, the cat was just where he is. Where could the mouse have moved from? Well, what are the adjacencies to where he is in this resolved state? If he's at 0, the only adjacency is 2. So he was at 2. Okay, can we resolve this state? Can we say that the mouse is here, it's his turn, in his turn he moves to winning? Is he already the winner here? Well, if we look at the matrix, we see that we can't say that because mouse at 2, cat at 2, mouse turn to play already has a winner and it's the cat, as we can easily see. Cat has already caught the mouse. Mouse is not going anywhere. So we cannot resolve this state again. It's already been resolved. No. So from this resolved state, I couldn't deduce anything. We tried. So to make things shorter, I'm skipping all the other deduced resolved states and I'm moving on to this one. Okay? With your permission, I'm just jumping to this resolved state and we'll try to deduce from it. So where's the mouse 2? Where's the cat 2? Whose turn is it? The cat, and the winner is the cat. So mouse at 2, cat at 2, cat turn, winner is cat. This. Let us try to resolve from it. Let us draw it. Sorry, mouse at 2. Yeah, I made a mistake. Mouse at 2. Here, mouse is at 2. Okay. So, let us try to resolve from it. So this is the resolved state, as drawn here. What states have immediately led to it in one step? Well, if here it's the cat's turn, then the one who moved was the mouse. Great. Where were they? If the mouse moved, the cat was just where he is. Okay, where could the mouse have come from onto this? Well, we look at the graph, and if he's at 2 here, then he could have come from 2 different places. So we'll have to examine both. The mouse either came from 0 to that state or from 1. Now, if you're raising an eyebrow, excellent, we'll get to it. Okay, let's examine one by one. We'll start by this one. Mouse at 0, cat at 2, mouse turn to play, moving on to losing. Okay, what's strange about this? Yeah, if the cat was at 0, he's already on his way to his vacation. He's free. Why would he do this? He's already drinking something on some beach, getting some sun. No. This is strange, but if I look at the metrics, mouse at 0, cat at 2, next player is the mouse, I don't have a winner here. It's still a question mark. I didn't, to begin with, do this because we said that it's always going to be the cat. If the mouse is at 0, it's never going to be the mouse turn because you remember. So am I going to resolve this now as a cat win? No. And what you need to do now is be patient until we write the code. As I said, we're going to relate to this. We're going to run a test case together and we're going to see why this situation doesn't matter and won't do anything, and we'll see it together. And I'm not drawing the mouse there to save runtime, and I'll show you that after I write the code with a test case. For now, you ignore this. mouse at 0 is already gone to freedom. We'll just relate to this one for now. So mouse came from 1 onto here. Okay, so let's see. Mouse at 1, cat at 2, mouse turn coming onto this state and losing. So does this state already have a winner in the matrix? So mouse at 1, cat at 2, mouse turn. No, it doesn't still yet have a winner. Can I deduce for it now? Can I say that already here it's the cat win? Well, in this graph, yeah, and we can see it with our eyes, right? We can see that there is no choice here but for the mouse to lose. Yeah, we can see. However, in real life, in bigger graphs, I mean, there may be more options here for the mouse to go to, more adjacencies. Maybe there are 3, 4, 5, 6, many other nodes onto which he can go, and then he should go there because this is not optimal, it's silly. He may want to choose another option if there is one. Here there isn't, but there might be. So, in this example, unlike the previous one, the one who makes the move onto losing, not onto winning like in the previous 2 examples. The one who moves makes a bad move because he loses. In this case, what we're gonna do is not immediately determine him as the loser because maybe there are other options. Maybe this is just one bad move, but maybe there were others he could choose. So when examining this, going from here to here, this means that we just need to decrement one move option for this player given those locations of them. When these are their locations, this is a bad move, but he may still have others. We need a counter for move options per player, per combination of where is he, a counter of move options for him to not lose. For every such bad option as here, we'll decrement one from the counter. And once the counter reaches 0, then yeah, okay, he doesn't have any options to move to given those locations. Where is he? He'll move whatever, he'll lose whatever he does. No move options left. It's on 0 after all decrementing. Then we can deduce that this is a lose state for him. He's at 1, he's at 2, it's his turn. Then we can say it's a loss. Now, these are the zeros you see here, and we're gonna fill it together. This means that in every cell of our 3-dimensional matrix, we don't only hold the winner for the state. Where is he? Whose turn is it? We're not going to hold just the winner. We're going to hold a pair. The winner and counter of move options for that player given their combination of positions. Where is he? Number of options to not lose. Let us initialize here and then we'll redo this example. Okay, so I'm going to initialize move options that are actually happening in real life. This means I'm not going to put any move options for the mouse for anyone in case the mouse is at 0, because if it's at 0, it's gone to freedom and nothing matters. I don't need any move options for anyone if the mouse is at 0, nor if the cat is at 0, because he's not allowed to be there. Why would I do any work for it? So I'm going to start from 1. So let's see. Let's work one by one. If the mouse is at node 1, mouse at 1, how many move options does he have? Just 1, because there's just one adjacency in this graph to 1. So when the mouse is at node 1, so wherever the cat is, I don't care for now, the mouse is at node 1, mouse column, he has 1 move option. If the mouse is at node 2, how many move options? 2. There are 2 adjacencies to node 2. So if the mouse is at node 2, he has 2 move options. Great, now let's work on the cat. If the cat is at node 1, how many move options? Cat at node 1, how many move options does he have? Just 1. There's just one adjacency to node 1. So cat column, node 1, 1 for every position of the mouse. And if the cat is at node 2, how many move options does he have? Well, here it's different from the mouse, because while the mouse could go either here or here, the cat can only go here because he's not allowed at 0. So when the cat is at node 2, he only has 1 move option, less than the mouse. Okay, now for every combination of where they are, let's do it together. So we're going back to these positions. When we know it was the mouse turn, right? He's at 1, cat at 2, his turn, and he makes the move onto this resolved state where he loses. This move is bad for him. So we go to the matrix to mouse at 1, cat at 2, and it's mouse turn, and decrement 1 from the mouse move options. Maybe there are many. This one is bad. So we decrement 1. Mouse at 1, cat at 2, mouse at 1, cat at 2, mouse turn to play, mouse move options, -1. -1 has got us to 0. This means that there are no more move options for the mouse for when he's at 1, cat at 2. He needs to move. There are no more options to move to without losing. As we can see in this graph, there is only this option. So since we got to 0, now we can deduce for this state that already the winner of the result state is already the winner here. Yeah, no other options. The mouse made a move and lost, and there are no other options. So already it's the cat. So let's see if this state is resolved, or we can also do it here. Mouse at 1, cat at 2, mouse turn to move, cat win. This state is not already resolved, as you can see, and it's a cat win. So now we can resolve it. And this is our goal state, so we have solved the question again. And this graph is a cat win. So this concludes our algorithm, and we saw that there are different behaviors when deducing for a previous state. Either the one who made the move made a move onto winning or onto losing, in which case we don't immediately declare him as a winner already in the previous state. We just decrement 1 from his move options from that combination of locations. Okay, so let us write the code. Here we have a main with some test cases. I'm calling the function test. This we're gonna run together after writing the code. This is this. This is it. Node 0 is just one adjacency, 2. Node 1 is just one adjacency, 2. Node 2 is 2 adjacencies, 0 and 1, and it's the cat win. I promised we'll talk about it, so we will have a breakpoint and we'll run this after writing the code. So this is our class. I have the input here. The graph is a vector where each index represents a node and holds a vector of all nodes adjacent to that node. Let us start by declaring our constants. So we know that draw is 0, mouse win is 1, cat win is 2, and now the index for the third dimension. Mouse 0 and cat 1. Great. Now let us determine the matrix, the game. So I can have a vector of graph size on graph size, but I don't want dynamic allocation. I want to be extremely efficient. So the maximum size of the graph is 50. It's not huge. I'm going to have an array. So where's the mouse? where's the cat? And the third dimension, 2, mouse and cat. And in each cell of this three-dimensional matrix, I'm gonna have a pair for the winner, either cat win or mouse win, and a size t for the counter of move options. It's a size t because size in a graph is size t, and it's also readable. Also for readability, we're gonna comment it. Now, I don't need to initialize it because it's an array of CPP. So the winners are by default all draw 0, and the number of move options are 0, and we're gonna initialize them in a second. Now, let's have a queue for the resolved state. We put all resolved states there one by one and add more as we go and pop them from there. So queue of an array of 4 ints. What will be in every index, in every element of the queue? Where is a resolved state? Where is the mouse in the resolved state? Where is the cat? Whose turn is it? Who's the next player? And who's the winner of that state? Now, I might say that this is like repeating data. I can just write 3 here, not hold the winner, just the state, and look at the game, at the matrix to find out the winner of this state. Just push the resolved state without the winner. But I don't want this extra access, and it's just one more int. I'm gonna hold it. Okay, now let us start with initializing. So first we're gonna want to initialize the resolved states, the ones that are pre-known without calculating anything. So all I need for this is the index of the cat. Where is the cat? Because in all the situations where the mouse wins, the mouse is at constant node 0. It's just the cat that can be anywhere. And where the cat wins, then they're together in the same place. So I just need a counter for the cat location. And I'm gonna start at 1 because it's not allowed at 0. Now let's set the winners. So if on the matrix the mouse is at 0, the cat is anywhere, and it's the cat turn. Cat turn only. It's the cat turn, then the winner is the mouse. Now, I don't just want to mark this in the matrix, I also want to push it onto the queue of resolved states to later deduce from it. So resolved states, push. I'm gonna do it in the same line because it's shorter, and also I won't make a mistake with this redundant data, the winner. I'm just doing it together. So mouse is at 0, cat is anywhere, cat turn, and this is the winner. Now it's an array, so. Okay, so we set it in the matrix and we pushed it into the queue. I'm gonna copy this line because now I need to set the situation where the cat wins. Now, pay attention that I don't need to do this. I mean, the cat wins if they're together, only if it's not node 0. I mean, if they're together at node 0, it's not a cat win. 0 is the mouse freedom. But I don't need to do it because my loop starts at 1, so I don't need this if. So if both are at the same location, cat, yeah, same index starting from 1, and it's the cat's turn, same location, cat's turn, cat's win. And I'm gonna copy this, same thing, but mouse turn. So it's both in the matrix set as a resolved state and in the queue of the resolved states to deduce from. These 3 lines conclude the drawing of the small pictures. The small pictures of the already known winners. Okay, now let us initialize the move options counter, and now I already need the mouse location as well, so it's an internal loop. I'm starting at 1. I don't need to count move options if the mouse is at 0 because he's on vacation, free. Okay, how many move options do they have? Well, depending when they are, it's the number of adjacencies to that location. So, game in index, where is the mouse? Where is the cat? Mouse counter of move options. Counter of move options is the number of adjacencies to arrays. Graph at index M. Cat move options. Size. Cat move options. Where is the mouse? Where is the cat? Cat move options. Move options are the number of adjacencies to array is minus 1 if one of them is the whole. The whole is not a move option for the cat, right? So if one of the adjacencies, like here, if the cat is here, there's just one move option, he can't go to this adjacency. So number of adjacencies to array is to the node minus all right. So this concludes the counting of the move options for each one. So here we have our matrix initialized and we can start deducing, trying to deduce for a goal state. So let's deduce as long as there is a resolved state to deduce from, while the queue is not empty. While the resolved state is not empty. In this loop, we'll take resolved states one by one, and try to deduce for the one-step BFS of the steps that led immediately to it, the states that led immediately to it. And if one of the states that we resolve in here will be our goal state, we will return. We don't need to continue. We'll just return at that moment. This means that if we're out of this loop and we haven't returned an answer, it means we could not deduce a winner for our goal state, and there's nothing more to deduce from, no more resolved states. And if we could not deduce for our goal state, then it's a draw. Now let's try to understand this. Why would this happen? Well, if there are situations, because let's look here again, in our matrix, there's one piece of information we're not holding. We know the counter of move options from where you are. If there are move options, we know the counter, and we decrement for each one where you moved and lost. But there is no knowing of what's already been visited. I mean, if there are more move options from here, I can go there, but I don't know if I've already been there or not. There is no visited recording here. So counters may not reach 0 because you could still go to other places and there's still options to go to. So counters may not reach 0. So we may have states that remain unresolved because you could go to a place where we already have been, and it's okay. And that's the exact meaning of a draw, okay? So if it happens that we could not resolve our goal state, it means that there was just somewhere going back and forth. It's a draw. Okay, let us start deducing. So let's pop the next resolved state from our queue. So what do we have there? We have, in the resolved state, where's the mouse? Where's the cat? Who's next to play? Who's about to move? And who was the winner in this state? Let's pop it from the queue. And now, we know, going back here again, we know that for each resolved state, there might be several states that led in one step to it, depending on where the one who moved onto here. The number of adjacencies in the graph of where the one who moved is now here. All the places from which you could make the steps onto here. So that's the only difference between all the states that led to the resolved state. And that's what we're going to loop over. All the places from where the one who moved could have moved from onto the resolved state. So I just need to see who's the one who moved. If in the resolved state the next one to play is the cat, then the one who moved was the mouse. So I need all the adjacencies to where the mouse is now. So graph, it index where the mouse is now. But if the next one to move is the mouse, then the cat moved. So I need all the adjacencies to where the cat is in the resolved state. Great. Now we can actually take one by one of the states that led to the resolved state. So in that previous state, previous, where is the mouse? Previous, where was the cat? Who was the one who moved? And again, we need to examine who is the one to move in the resolved state. If the next one is the cat, then the mouse moved from somewhere. The cat was where he is. The mouse moved. Otherwise, if the mouse is to move in the resolved state, then the cat moved in the previous state. So the mouse was where he is. The cat moved from somewhere adjacent to where he is now. The cat moved. So now we have the previous state in our hand. And we need to figure out if we're allowed to resolve a winner for this state. So what are the conditions for resolving a winner? Well, there are quite a few. We may resolve the winner, first of all, if that state is not already resolved, right? We don't override the winner for an already resolved state. Also, the cat is not allowed at 0. If in the previous state the cat is at 0, I'm ignoring this. I'm not resolving anything. So let's start with this. If cat, previous. Only if the cat wasn't at 0 and that state is not already resolved, if it's still a draw, what other conditions do we need for resolving? Well, either the one who made the move on to winning, so already there he was the winner because it was his turn and made the move on to winning, or he made the move on to losing and that was his last option to move from combinations of where they are. And so yeah, no other options. So we can resolve for these two states. So it's going to be an or between them. I'm going to give them a parenthesis. It's this or that. So either the one who moved on to winning. So I can ask if PP is the mouse, moved on to winner. Winner is the mouse. Or PP is the cat and moved on to winning. The winner is the cat. But to cut things short, I'm just going to ask if that player who moved is the one who won. If player +1 is the winner, because if we see our constants, mouse move, mouse win. 0 + 1 or 1 plus 1 for the cat becomes 2. So it's just this simple math here. So if the player plus 1 is the winner, or, so this is if you moved on to winning. 0 plus 1 equals 1, or 1 plus 1 equals 2, or let's decrement from his move options. Move options, and we have reached 0. Yeah, so we can deduce. These are our 4 conditions, this and this and this or this. These are 4 conditions for deducing for this previous state. However, if this previous state is our goal state, we're just returning. Mouse at 1, cat at 2. Player was mouse. Yeah. Bye-bye. We have an answer. But if it's not our goal state, we just mark it in the matrix as a resolved state, push it into the queue of resolved states, and continue. So I'm gonna copy a line from here with your permission and just change it. Resolved state push. Where was the mouse? Where was the cat? Who was the player? Where was the mouse? Where was the cat? Who was the player? And a winner resolved for this state. Okay, so if we're out of this loop without having returned, then it's a draw. Okay, let's see if this runs first. Great. And before we run it on LeetCode and everything, I have promised you something. We'll do that, then we'll talk about complexity, still some things to do. Okay, so I promised to talk about not doing this. Not doing this. Right? Right? Not drawing the mouse. Not doing this. Right? Okay, so let us see. So I'm putting it in a comment. Okay, I don't want it. I'm not putting it, right? Not putting it. And here we have this exact example. I'm gonna put a breakpoint right after it. I just want to run this one, and I'm gonna place some code that I prepared here. I'm in the loop of resolving one prev state after the other prev state of the resolved state. So I'm just printing here the data of the resolved state and of the previous state that we're examining. Okay, take a look at it. So I'm running now. And as you can see, we got to the situation where the resolved state is, as we had in on the paper, mouse at 2, cat at 2, next player is the cat, and the winner is the cat. And we said, remember, both here, and the winner is the cat, and the previous state was this, and we said, how can it be? The cat already wins here. Well, here you can see why it doesn't matter. Because look at the mouse move counter. Look at it. Because when the mouse does this, it's just -1 for his move options for when he's here and he's here and it's his turn. It's just -1 for move options. Since my move options are a size T, this got me to a huge number. This will never reach 0. We will never say that the cat is a winner there. Also, if I set it not as a size T but as an int, then it will be a -1. Okay, this is a warning about type conversion, but it was -1. It will never get to 0. So we will never say that the cat is the winner where the mouse is at 0. It will never happen. But Why still get to -1 and this huge number? Because let's go back to size t. It doesn't really matter for this example now. Let us put this line. Now I'm also initializing the mouse as the winner when he's a 0, it is his turn. So remember what we had here, this printing, resolved and previous, this printing, and I'm running now, and look how many printings I have for this tiny graph, because I have many states that are resolved and I'm deducing from them for nothing. So this is more runtime because I have resolved states where the mouse is at 0 and it's the mouse turn. Why would I do that? So as you can see, I just need to be aware of the things that happen here, but I can definitely not have this line because it's not going to happen. Okay, so now let's remove this printing. And before we're going to run this on LeetCode, let's talk complexity. So let's start with the space complexity. So for the matrix, it's just O of 1 because I chose to avoid dynamic allocation. It's just 50 on 50. Doesn't depend on the graph size, O of 1. However, the resolved state, this Q, may have all the states that might happen. We may have to push all possible states there. And all possible states are graph size on graph size. Where is he? Where is he? 2 times, his turn or his turn. So I can ignore the 2 times, it's just where is he or is he. So this is a square n. Graph size on graph size. The resolved state is square n. So the space complexity is square n. Now, time complexity. For the initialization of our matrix, it's also square n because the outside loop is on this graph size and the inside loop as well. So square n. However, the deduction loop is the loop in which you deduce from our states is we're going all over the Q, which is we know square n, and each time we loop over all the adjacencies of the one who made the move to where he is now. So this is also n. So because this is square n and this is also n, because a node may be adjacent to all others. So this is already n to the power of 3. So this is the time complexity, n to the power of 3. Now let us run this on LeetCode. And I ran this many times because I tried different variations to see how they affect the runtime. I also tried like holding 3 here and accessing. I think actually it was fast. I don't remember, but I didn't like it because I wanted just 1 line. So I put it together, but I ran it many times and it was 100% many times. Why am I telling you this? Because of Murphy law. Now together it will surely not be 100%, would it? With audience. But I did it many times and it was 100%. So I just have to trust Murphy to be busy somewhere else right now. Okay, let us run this. Please. 89. No, that is just horrible. That is just horrible. I don't accept it. 98. We all know that it's not really precise, but I got 100% many times. I leave it with the 98 here. And space complexity 82. Assume because of the array of 50 on 50. So I'm happy with this. I'm happy with this. And I hope you enjoy this. Please like, subscribe if you wish. And thank you for joining me on CPP in Pajamas. See you next time.